So the talk will be recorded and posted on Theorem website. Well, it's a great pleasure to welcome.
Is that a warning?
No, it's just if someone wants to stop the video on the camera or something. It's a great pleasure to welcome Anush-Tserunyan from McGill. She'll speak about ergodic theorems along trees.
Thank you. Thanks, Dima, very much for inviting, and thanks everyone for coming. So this is all joint work with my student Jenna, who's right there. So it's about ergodic theorems. I mean, classical ones. I'm sure you've seen, but it's about a new ergodic theorem that we very recently proved. Okay, so. Let me start with the setup. I'll bore you a little bit just so that we're on the same page with notation and my terminology. I'm sure you know all this stuff anyway. So for let x mu will always denote a standard probability space by which you can just think of as, just a 0-1 interval with a Lebesgue measure, or for example, the space of all binary sequences with the coin flip measure to the product. So it's a product measure. So say coin flip to the n. Same coin flip, say 1/2, 1/2. To the end. So this is this another standard Borel space, standard probability space. They're all isomorphic. The non-atomic ones are all isomorphic to each other. Oh. And I'll give an example to keep in mind, or two examples maybe. So example. So I mean, everyone has their own examples, but typically in this talk, I'm going to be dealing with non-one-to-one transformations. So they're going to be countable to one. So that's why this example is maybe good to keep in mind. So it's 0-1 and mapping x to 2 times x mod 1. This is so it's basically, I mean, you can think of it as you have some dou. This is the 0-1 interval. You transform it, you make it longer, you smoosh it to make it longer, so it's now 0-2, and then you cut in the middle and paste on top of it. Although my husband, who bakes bread, at least says that you shouldn't do that. You shouldn't cut the dough. So okay, this is 1, 2. So this is the kind of example you want to keep in mind. So this is 2-to-1. Another example, because I like more discrete spaces, like, I mean, not discrete, but at least more disconnected spaces, so that I can do combinatorics on them, is this example, the example of a shift map. Another example is the shift on the 0-1 to the n. So it is defined by, so you map 0-1 to the n. In fact, I'm going to write 2, okay? So after all, I'm a logician. 0-1 is just the set 2. So 2 to the n, 2 to the n. And it maps the binary sequence xn to, forgets the first coordinate. So the sequence xn plus 1. Okay, this is again clearly 2-to-1. And as a matter of fact, I mean, this I just gave actually only one example. So these are isomorphic. And the isomorphism you would get from one map to the other map by mapping the real number x to its binary representation. So I'm just giving you these examples in case you like to think of it this way or like to think of it this way. Either way, these are 2-to-1 transformations, measurable transformations, okay? All right. So next notion is I'm going to assume that T is probability measure preserving or just measure preserving, I guess. So for short, I'll just say PMP. That means when it acts on it, the measure is preserved. Precisely, it means that for any measurable set, the measure of that set is the same as the measure of its pre-images. Well, I mean, it's not typically not one-to-one, so I have to require pre-images, not images. And in that regard, like, you know, with this definition, either of these maps are measure preserving. Okay, so, and this map would be, yeah, never mind, sorry. All right, so now let's understand on the level of points, what does measure preserving mean? More combinatorially on the level of points, as opposed to the definition is on the level of sets. So it means intuitively that the weight of a point X, whatever I mean by weight, I mean, this is nonsense, there's no weight, but if you intuitively think of a weight of a point in the measure space, it is the weight of a point is equal to the weight of the set of its pre-images. That's what measure preservingness means. And in fact, it's not an intuition, just I'll make it precise later what I mean by this. So there is some function on the pairs of points in the same orbit that measures the weight, the ratio of weight of one point with respect to the other. And so it measures the anyway, so it measures the fact that the weights are different. Weights of points are different. So here, let me draw what I mean. So if I have a point in the space X, so let's say this is T of X, this is the direction of T, and I have its pre-images. So this is again the map T. Oops, sorry, I'm drawing the pre-images. And so on. And now if you take this set of pre-images, so this set and this point X have the same weight. So this is 1 kilogram. This is also the whole thing is 1 kilogram. Okay, that's the intuition. And indeed, so if you look at, so I'm just giving you again intuitive things, okay? So I'm not, there is no math yet. So if we look at the shift map, or equivalently the Baker's map, we as above, we have that if you have a point X, then it has two pre-images. So X is a sequence of zeros and ones, and its pre-images are, you know, you either forgot the 0 in the beginning or you forgot the 1 in the beginning. So this is 1 followed by X and so on, right? So it's this binary tree. So I'm drawing one orbit of like, this is the shift of X, whatever, and so on. And it turns out that, for instance, if I take the measure like here, 1 over 2, 1 over 2, then the weight of X, if you declare the weight of X to be 1, so these weights are relative. So there are no absolute numbers, but relative to X, these points will have measure 1 over 2 and 1 over 2. And then these would be 1 over 4, 1 over 4, 1 over 4, and so on. Not measure, I mean weights. And then this guy, the image of X would have measure 2, weight 2, sorry. Okay, so and I'll make this notion of weights precise, like this comes from some radon-Nikodym derivative. But I mean, so far, all I've said is that T is probability measure preserving, and I try to explain the pointwise intuition behind that notion. Okay, so and then we call a set B invariant, or I mean T invariant, if it is a union of full orbits, but with like both directions, okay, pre-images and images. So in other words, it is, if you just take a pre-image of B, you get B back. And something that I think about a lot is, so the equivalence relation that I just defined, being in the same orbit, is denoted by ET, okay? And there is a notion of measure preservingness for equivalence relations. And funny enough, even if T is measure preserving, the equivalence relation isn't, if it's not, unless T is 1-to-1. So this is why we have different weights. See, you have, if weight of X is twice as big as the weight of its individual pre-images. Okay, so just defined what invariant is, and just let's recall that T is called ergodic if every invariant measurable subset is either null or conull. So basically, this is a form of transitivity or a form of measure theoretic density. Measure theoretic transitivity or measure theoretic density. Okay, so ergodicity means I can't split this action of T into two significant parts of the space. Let's move on. Now, I want to right away remind everyone about the first ergodic theorem there is, or pointwise ergodic theorem there is. So Birchhoff's ergodic theorem, it just says that for any PMP, so probability measure preserving transformation T, like in the previous slide, so that this transformation is ergodic if and only if, whenever you have an L1 function, so something to measure on the space, if you now, for almost every point, like if you localize yourself to some point, a point, and this works for almost every, and look at the interval of its images in front of it, so x, tx, t squared x, and so on. So if you take n large enough and consider the average of this function over this finite set, so the sequence of these averages converge precisely to the expectation of f, so to the mean of f, as n goes to infinity. So somehow, I mean, this comes from the fact that, as I said, like ergodicity is some notion of density, measure theoretic density, and L1 functions are measure theoretically, I don't know, continuous functions. So this makes sense. Okay, so this is the first version, and right after this, let me state a special case of our theorem with Jenna. Now, so this is now a special case, but I want to, explain the special case before I go to the general case. Okay, so it's very similar to the previous one, except that instead of taking images of the points, I'm taking pre-images of the points. So I'm taking bigger sets and not just the interval in front of x. So, and we have to assume countable to one to even make sense of this. So you assume that the PMP transformation is countable to one. And the theorem says that it's ergodic if and only if, again, whenever you fix an L1 function, and for almost every x, for almost every x, if you look at its union of its pre-images, here I'll make it bigger. So if you consider this set that we denote by triangle, if you take x, then you also take the set of all pre-images, and then the further pre-images and take union. So basically you take this complete tree, so triangular, so the triangle behind the point. Then I want to say the average of the function in this set converges to the mean of the function. However, these are not just averages, these have to be weighted averages, otherwise it's simply false. So, and the weights here are coming from this this thing that I told you that, here. These are the weights I was talking about, and I now will have to make it precise, okay? So let me go back to this. So these are these weights. So here the weights are assumed, as I said, measure preserving means that the weight of x is equal to the weight of the set of its pre-images, so which hence also is equal to the set of its second pre-images, and so on. So all the weights of this are 1 if you declare the set weight of x 1. So, okay. So like my color scheme is such that, the weights I denote by blue, and in fact this n is, I treat it as a weight as well. So this upshot is basically Birchhoff's theorem says that if you take averages in front of x, they converge to the expectation of the function. Our corollary, or special case, says that if you take pre-images behind x, so or like sort of these sets behind x, then the weighted average of the function converges to the expectation. And let me also point out that if we go back to Birchhoff's theorem for a moment, a priori, before the theorem is proven, one needs to know, in order to prove it, that this limit, if exists, has to be invariant. So that's what we would want to show. So, or if you take the supremum of this sequence, you want it to be an invariant function. So in this case, the invariance is clear because if you have, you're measuring your average on this interval x. Now let's look at what Tx would do. Tx would measure it on this interval, say. So, and these two intervals, maybe I should draw by another color. I don't know, purple. So the interval for Tx would be something like this, right? And they coincide on this large set. And so the only difference would be the point here and the point here. And this difference is negligible compared to the length of the interval. So it is clear that in the limit, or like if you take the supremum of this, you will get an invariant function. However, that is not the case in this theorem. This is not clear why it's invariant. For instance, look, if you look at this point, for this point, it's looking at averages over triangles behind it. And this point is looking at averages over this huge triangle behind it. But there are so many extra points here, like this entire set is extra. So there is no reason a priori why this triangle should calculate similar or close averages to this triangle, or sorry, to like this bigger triangle over here. Okay, so somehow it's a bit weird what's going on here. However, this will become clear when I do the general case, not the special case. Okay, so now I promise you to explain this weight business. And so these weights are given by the so-called Redon-Nikodym co-cycle on the orbit equivalence relation. So on the pair of points with the same orbit. And this co-cycle is induced by the measure mu. So okay, let's understand this. And also along the way, give an operator theoretic formulation of this special case so that it makes, maybe it rings more bells for people in this audience at least. So, so once again, so T be a countable-to-one ergodic PMP map. And I'm taking the standard thing like the Koopman operator of this map. So it's just defined on L1. It's a function on L1 and just like spits out its shift. So like it shifts the space by T and then applies F, the usual thing. So, and Birchhoff's theorem just says that if you restate it in terms of the Koopman, it just says that if you keep applying this operator all over and over, is pointwise converge to the expectation of F. Okay, so that's what Birchhoff says. Now let's again remind you that let's denote by E sub t the equivalence relation of being in the same orbit of t. So intuitively, this, as I said, this measure mu induces a function, which I denote by rho, on the equivalence relation itself thought of as set of pairs. So this function eats a pair of points in the same orbit and spits out a positive real that is supposed to be the weight of, so the real should mean the weight of the point y over the weight of the point x. So I, symbolically denote it by this d mu y over d mu x. And in fact, this, so this rho is a cocycle. So as I said, it's a cocycle. Cocycle means that if you have rho xy times rho yx, rho yz, this should be equal to the rho xz, which this notation makes it trivial, like this notation. So basically what I'm saying is that these parts, like the denominator and numerator, they cancel. And the point of this cocycle is that it makes maybe I don't want to say what it does. Never mind. So anyway, so this is how you should think of it, and it exists. So so it makes it makes mu rho invariant. So it corrects, this cocycle corrects the error of invariance in some sense for the equivalence relation. But anyway, so let's see what I wanted to say here. So these are this function. This always exists. So such a rho always exists. Rho always exists by the Redon-Nikodym theorem or derivative, and a theorem from descriptive set theory called Luzin-Novikov. So it's a uniformization theorem, old uniformization theorem, Luzin-Novikov. Okay, so it's just like a little advertisement for descriptive set theory, and I think that's about it for this talk, as far as advertisement goes of that subject. Okay, so but this Redon-Nikodym derivative gives us explicit form of the transpose of this Koopman operator. So the transpose of the Koopman operator is given literally by looking at the point x, right? I'm evaluating at the point x. So what you should do is look at all preimages y of this point x and take the sum of the values of the function weighted by this cocycle, where the weights are the relative weight of y with respect to x. And so, for instance, if you had an operator defined using a Markov chain, here you would see the transition matrix and the initial ratio of the initial distribution. So something that maybe is more familiar. But this is a very general thing, and not just for Markov chains. Okay, so and this operator is a type of Ruel transfer operator. I mean, literally by its form, where this function is taken to be the cocycle of this measure, and the Redon-Nikodym cocycle of this measure. And it's also a Markov operator, which just means that it's a positive L1 and L infinity contraction, and it fixes one, the constant function one. So by a general ergodic theorem for Markov operators, this kind of things, this kind of contractions. So Dunford and Schwartz have a theorem for it that say that such operators, if you take these ergodic averages of these operators, the limit exists almost everywhere. But of course, this is too general to tell you what the limit should be. In fact, it doesn't even tell you that the limit is an invariant function under T, okay? Of course, it is invariant under application of this adjoint, but not under T. And what our theorem from previous slide says, this special case says that this limit is in fact the expectation of the function f almost everywhere. So this is just the only contribution of this special case, I guess, for this adjoint, and also the fact that one can, this is easy to calculate that the adjoint is this. So this was the operator theoretic formulation. And now let's understand. So now that we have these weights, I just rewrote only once what I mean by weighted average. So by weighted average, this is the theorem from the previous slide, that was the special case of our general theorem. I'm just replacing the English phrase weighted averages by the actual formula. So we take all points y in this preimage triangle of height n, and we're summing the values of the function times the weight of that point relative to x. And I'm dividing it by the total weight, and y is total weight n plus 1, because this triangle of height n has precisely n plus 1 columns, and each column has weight equal to x, so relative weight 1. So you get 1 plus 1 plus 1, and so height 2 gives weight 3. So this is the theorem, or like this special case. And now I'm ready to move on to the general case. And this picture I took on campus maybe in September. So I couldn't believe it was right there for me. or I guess this. Anyway, so now trees come in. So how we prove this special case, and in fact, this is a much better theorem than the special case, is in fact that what is true is not only that you can get these averages over these like, you know, very canonical full pre-images like these triangular sets, but in fact, if you take weighted averages along any subtree of this of the pre-images, so like look behind the point X and take any subtree, even if you omit some, you know, for instance, this tree I drew, you can omit this branch completely, and so you never touch these values. So if you take along any subtree, as long as the total weight of these subtrees go to infinity, the weighted averages over these trees converge to the expectation as usual. Yeah. So the I mean, new thing here is that the shapes that are good for us, that the theorem handles, are no longer so regimented. Like it's not just, you know, nice complete like pre-images behind it, but it's more of a quantitative result. Like the shapes are all trees, different kinds, whichever you want, as long as their weights. So this is the quantitative thing. So the weights go to infinity, you know, the averages are fine. The averages are going to be close to the integral of f. And this is now not too hard to see that this sequence is an invariant, it's not a sequence now. I mean, it's, you know, I'm taking it over the whole class of trees, like whatever trees of finite diameter, okay? So it's not a sequence, it's like a whole, I mean, it's a directed set, or if you want. So now it's not hard to see that this is invariant, because if the average over this tree is not so different than the average over, like, you know, you put one more edge here and take the average over this tree. So then it's not easy to see that the averages of over all trees for point X should be the same as the averages over all trees of the point Tx. Like, so if you put a sup here, say, you know that that sup function would be invariant. And to be honest, this is why we came up with this tree business, because we wanted to prove the special case originally, and we couldn't figure out why it should be invariant. And you know how sometimes when you want to prove something by induction, you actually have to assume something stronger for the induction to go through. This is such a thing. So the induction thing was the trees, but then we realized this is much more interesting theorem. So forget the special case, I guess. Okay, so now just to illustrate this theorem on one of our examples, so the shift example. For the shift example, it's because the measure is, I guess, a Markov measure. In fact, if you take the 1/2 measure, then you can calculate these weights explicitly. The weights are, I told you what the weights were. Like if you declare the weight of x1, then the weight of the pre-images are 1/2, 1/2, and the weight of the image is 2, and so on. So the weights are clear here. And what we get what our theorem would give you is that if you now consider, so we're considering the space of binary sequences with this product measure, okay? If you take any, and the map we're considering is the shift map, which is just forget the first coordinate. So what the theorem says is that for every L1 function and for almost every point, if you look at the averages, so to take any tree that is a syntactic tree on the alphabet 0-1, so it's a set of words on 0-1 that form a tree when you write them syntactically. So let A be such a tree. If you take the averages, weighted averages over these trees, in which here the weighted average would be just, you know, for each word, binary word, finite binary word, the weight of that word, so with the weight of, say, this point, the weight of this point, say, is, so who is this point? This is 1-1. Or like, okay, let's do this point. This is 0-1, okay? So the weight of this word is just negative 2 to the minus the length of the word. So in this case, it's 2 to the minus 2, yeah. Okay, so this is what it says. So this is the weighted average, and this is just denotes the total weight of the tree you took. And the theorem says that as long as this weight of this, so this weight goes to infinity, this average should converge to the expectation. So yeah, so I mean, you know, so I often get asked, what if you just take one branch? I mean, it's inconceivable that that one branch should give you the correct ergodic averages, and it doesn't. Like if you consider the weights on one branch, this is a summable sequence, so it does not go to infinity. So of course, well, yeah, one branch won't give you the correct averages, but as long as you know your trees are enough bushy along the way, you will get the correct ergodic averages, and this is the measure of bushiness, I guess. Okay, so this is an example of our theorem. And our theorem, let me go back, unlike the special case, this does not have an operator theoretic formulation, because I mean, the operator theoretic one like requires determining some transformation. For our case, it was just like taking all the preimages, sum over all preimages, and then iteratively applying this. I mean, what I'm considering here is not an iterative sequence, like it's a directed class of trees. So in fact, there is no possible way that a single transformation would give you an ergodic theorem like this, or like a statement like this. So there is no, at least I can't think of an operator theoretic formulation of this. So you have to stick to this combinatorial picture. Okay, yeah, this was the example. Now let's switch gears and move on to group actions, which is really what we were after. But this other theorem somehow is what drives the theorem that we prove for group actions. Not just drives, but yeah.
Can I ask a quick question?
Sure.
There are some polynomial ergodic theorems, like you average not going forward, you average not at overall integer powers of t, but overall, let's say, squares, t to the n squared or something.
Yeah, so they are still along the lines.
Can there be a backward version like you're doing of such a theorem, and so how will it look in principle?
Yeah, in principle it can be. I mean, we can only handle tree shapes, right? So that's what I said. But in principle, for instance, I mean, in principle, one could hope to handle other shapes, in particular shapes that would be carved out by polynomial indices. If I understood what you're saying.
It could be some kind of forest or something, I mean.
But a forest we can handle. If it's a forest, I mean, not forest, sorry. I mean, the theorem should have to, whatever shapes you're giving me, it should contain the point X maybe. I mean, it doesn't have to, I guess. It doesn't have to. No, sorry, I take it back. Yeah, I take it back. I mean, what would be interesting is, for instance, is it possible to have somehow an ergodic theorem like along spheres, like along the even spheres as you go back, for instance. Okay. So that would be interesting. I don't have a counterexample, and I have no idea how to prove it. Our theorem, so there is some tiling we prove, and there we don't know how to tile with spheres, but we know how to tile with trees. As long as the trees contain the root, we know how to tile them. How to solve this tiling problem. I mean, when you prove ergodic theorems, there's usually some Vitali covering or tiling argument, and it's also present here very explicitly. Okay, so please ask me if you have other questions, because otherwise I'll just continue. So now application to group actions. Let's review ergodic theorems for group actions, the existing ones. Bufetov ergodic theorem, if you just write it for a one-to-one transformation T, it just, by measure preservingness, this transformation should just be an automorphism of the measure space X. So in fact, you can just consider the action of Z, where the automorphism is just the action of one. So Bufetov ergodic theorem just translates to when like a PNP action of Z is ergodic if and only if for any L1 function you take, this averages over, now I wrote it group theoretically, right? This set Fn, which is just the interval from 0 to n. So the Fn times x gives you precisely this interval in front of x. So the averages over this finite set converges to the expectation. And so let's understand these theorems. Like why are intervals important and why do they work? So the reason why they work is because they are almost invariant, right? If you have an interval, like a long interval like this, and another interval like this. So if you move this interval to this direction, the two intervals coincide on a very large set, and the only points that fall off are this point, that this point is bad and this point is bad. But who cares about 2 points over n many points? So the error is negligible. So that's the reason that intervals work, is to guarantee. So this makes the limit, or even just the lim sup of this sequence, an invariant function. And that's very important in proving the ergodic theorem. So, okay, so what other groups have these sort of subsets that have, these sort of invariant subsets with small boundaries, and so here, the boundary has only 2 elements constant, but I mean, in general, it can depend on the number of points, but can still be small relative to the whole set. And so these groups are precisely called amenable groups. These are precisely the groups that admit a sequence of sets, Fn, finite sets Fn, called Fellner sets. And these subsets, these Fellner sets, become, in a precise way, more and more invariant. And so you can use these Fellner sets to get a theorem here, which is what Lindenstrauss did. So Lindenstrauss proved that for for so-called tempered Fellner sequences, so special kind of sequences like this, the pointwise ergodic theorem holds for all amenable groups, and every amenable group admits a tempered Fellner sequence. In fact, any Fellner sequence like this admits a tempered Fellner subsequence. So this is basically Lindenstrauss completely handled amenable groups. And it seems from what I said that amenability is a necessary condition to prove an ergodic theorem, because you want the boundary of the sets to be small so that you get that these averages become invariant. Like these are invariant under the group action. However, mathematicians find a way to prove more theorems, and there are ergodic theorems for non-amenable groups. So let's understand them. So a typical non-amenable group, the only one I can work with, is the free group on 2 or more generators. So its finite subsets have large boundary because it's a tree. I mean, you can think of the Cayley graph of the free group. So for instance, let's take a ball. So a ball in the free group based on at identity. So I drew right now the ball of radius 3. Closed ball of radius 3 inside the free group, and I drew the boundary, so the leaves by green, and you can see that there are more leaves than non-leaves, or at least as many. So I think it's more. So the boundary is really large. The boundary of balls in the free group is really large. But we want to prove an ergodic theorem, you want the boundary to be small. So what do? We artificially make the boundary small. How we do this? By just assigning weights. So we make the boundary small by assigning weights so that each sphere of the free group gets weight 1. In that case, so here, for example, so you can think of this as a random walk on the free group where you're not allowed to walk backwards. So you stand at the identity, you have, so it's a uniform. So you have equal probability to go either direction. So 1/4, you go here. And then here you cannot come back. So the only thing you can do is to go this direction. And this is probability 1/3 each. So here, the weights of this point, the probability of appearing at this point is 1/12. And so on. So like you have equal probability here, equal here. So this is equal distribution. And so the weights or this distribution, so this becomes a distribution on each sphere. So here is like the one distribution. This is the uniform distributions. Okay, and all the spheres add up to 1. Each sphere adds up to 1. So yeah, it's a random walk assignment of weights. And now with this assignment of weights, the boundary is small compared to, like, if you take a ball of radius n, its boundary is only the last sphere and its weight is 1. So you get 1 over n. And in fact, like if you want a thicker boundary, let's say, like, you know, so whatever thickness of the boundary you choose, you can take a big enough ball such that that thick boundary is small compared to the size of the ball. So the weight of the ball. So that's it. And so this is what they do. And yes, it works out. One can similarly prove an ergodic theorem. And this is a theorem announced by Grigorchuk in 87, or maybe earlier. But so it certainly he proved it first, and independently Nevo proved it too in 94. So it just says that, so whenever you have a probability measure preserving action of the free group FR, and this means that each group element preserves the measure, like the action of each group element preserves the measure. So this action is ergodic if and only if, again, for any L1 function for almost every x. If you take, so we're taking these weighted points on the free group. Okay, so on the Cayley graph, the points are weighted. So it says that if you take the average of the function along the balls and you weight the points in the ball by these uniform weights, so like I described, so here are the uniform weights, and this is the ball. Then the weighted average, so it's like, you know, the sum times the weight divided by the total weight. The total weight is n+1 because the closed ball of radius n includes n+1 spheres. So any sphere has weight 1. So okay, so this says that the weighted average converges to the expectation. Now this is Grigorchuk and Nevo theorem. So what other theorem are there? So this was just theorem having equal weights. However, I mean, we don't stop here. So somehow equal weights work, but maybe other type of random walks would also work. And it turns out that it's true. But so let's consider Markov chains for a moment. So just to remind you, so let's fix a set S, which for us will be the generator set of the free group. But in general, this is some finite or infinite alphabet or set of states, so-called. So a Markov chain is a random walk on S. So this is the random walk. And it is defined by some initial distribution and a transition matrix. So here, in this picture, the initial distribution, so we have 3 states. I should say many of the pictures I stole from Jenna. I should maybe acknowledge since she's in the audience. So this is particular. This example was completely stolen from her. We have three states, and in the initial distribution on being at each state, this one is 1/4, 1/2, 1/4, and these on edges are given the probability of transitioning from this state to the other state. So we have some initial distribution pi, which is, I guess, 1/4, 1/2, 1/4, and some transition matrix. So I guess I will do it. What is it? So if this is 0, then we have 1/2, 0, 1/, does this add up? Yeah, 1/4. And so on. Okay, so this is how you build this thing, and what you get. So this gives a probability distribution on each collection of word of fixed length, because, like you say, you start from something and then you move around, you get some word of length n, and you get a distribution on the set of words of length n. And this distribution is given precisely by this, whatever formula, you know, this is the initial distribution, and then you multiply the transition probabilities. Okay, so this gives weights on the set of words. And so these words, these weights, introduce nothing but a probability measure on the space of infinite sequences. So as I said, it's a random walk. So you do get a probability measure on the space of infinite walks, so infinite sequences. And it is also denoted by P. So I mean, you know, in probabilistic language, you just have a random walk and you consider infinite random walks and you get them. This is the measure. And so this Markov chain, yeah, so I forgot to say, when you have probability, you know, you start with initial probability distribution, and now you want to see what is the probability distribution after being at a given state after n many steps. So the probability distribution of being at a given state is after n steps is just you apply this transition matrix n times to the initial distribution. Okay, and so what I'm saying is you would call a Markov chain stationary if the probability distribution of being at a given state does not change. You start with pi. Oh, I guess I should have applied the matrix the other way around. Sorry. Oops. Okay. So if you start with distribution pi and keep applying p, it doesn't change. It stays the same. In the dynamical language, this just says that the Markov chain is stationary if and only if this probability measure on the space of infinite sequences is shift invariant, where shift is our old friend, shift to the left, okay? And this is important because I only know how to handle invariant measures. And so now, knowing this, the best result was Bufetov's theorem from 2000. It says that, so take some Markov chain on the set of standard generators, symmetric set of generators of the free group. So there are two R elements here, 2R. A PMP action of the free group is ergodic if and only if, again, so for any L1 function f, if you take the averages of this function along the ball of the free group, just like in Grigorchuk-Nevel theorem, but now the ball is weighted by this like Markov chain, okay? It's a special Markov chain. It's stationary so that the shift action is invariant, and there are other assumptions. So you take the average of the function along the balls in the Cayley graph of the free group, weighted by the Markov chain, and these weighted averages still converge to the expectation of f. Okay, so this is, and so the weight of a ball is ball of radius n is n plus 1. Okay, so this was sort of the best result before, and in fact, Bufetov's result is a bit more general. It is proven not just for free group, but a free semi-group. So your transformations don't have to be invertible. Now, so our result is using the backward ergodic theorem from before, like this weird backward tree ergodic theorem. We are able to prove a much stronger version of this, which says that, again, so you can weight your free group, the Cayley graph, by some Markov chain, satisfying some natural condition. Then after these weights, if you consider weighted average, so again, a PMP action of the free group on R generators, where R is finite, by the way, necessarily. So so consider a PMP action of the free group. It is ergodic if and only for any L1 function f, if you take its weighted averages along any subtree of the Cayley graph rooted at identity, so any finite subtree of the Cayley graph, then these averages would converge to the expectation of f as long as the weight of this tree that you take, these trees that you take, converges to to infinity. So instead of considering these very regular balls, like specific balls, you can take any tree, doesn't matter, as long as the weights go to infinity. So I guess that's our theorem. And yeah, I should have mentioned right in the beginning, this is the first letter of my last name in Armenian. I decided I'm going to advertise my language as much as possible. So yeah, and this is also thank you in Armenian. I promise this is not a swear word. Well, thanks. That's, I guess, the end of my talk. Oh, wow. You know how to read? Who said
you
this?
have some additional requirement with respect to Bufetov or not about probabilities? Yes, this one.
Yes. We do. So Bufetov's one is weaker, so it gives more Markov chains. There is a high chance that if we understood actually what he's doing, we would be able to also get the same Markov chains. But basically, neither of us knows enough probability to handle this. So I mean, we haven't delved in it too much. But so the probabilities, the assumption that we have is that the Markov chain has to be stationary, and the initial distribution has to be positive, because otherwise you just lose a generator, and so you can't claim ergodicity after you lose a generator. So that is necessary. But then we also require that the transition matrix is positive unless you're transitioning from an element to its inverse. So those have to be 0, like I'm not allowing backwards. So this random walk cannot go backwards. But so otherwise it's like non-zero. You have to give the probability to go any direction. So yeah,
but Bufetov allows such transition.
Bufetov allows such transition because he, as I said, he in fact proves it for semi-groups. So there is no even inverses to talk about. And so he allows such transitions, but he assumes, he assumes strict irreducibility. So this is even stronger than irreducibility, which means, so that means that maybe he gives this probability 0, but somehow he's able to go to that element by how should I say this? I mean, like, it can't completely destroy a direction forever. So maybe like you keep going in this direction, but then you have to allow going into this letter after some point. In the sense of, like, this is an irreducible Markov chain.
What is strictly reducible?
Strict means that P times PT is irreducible. Yeah, so it's even stronger. Yeah, but so as you can tell, I don't understand this requirement well enough yet to be able to say whether our methods handle that.
But your condition,
my guess is probably our condition is definitely strictly irreducible, because we demand that all the entries are positive, except for when you're moving from a generator to its inverse.
Anush, I wanted to ask, how about mixing and correlation decay, kind of spectral gap type questions?
We haven't considered any of these questions. Mixing, So mixing, we use mixing of the shift action of the shift map in order to deduce this theorem, basically. So the way we prove this theorem is we want to apply the backwards theorem. So we're given a group action, and we're trying to build a transformation for which, like, the backwards ergodic theorem for that transformation somehow gives this theorem. So the transformation we take is the following. So we have this space X. So we take X mu product with the shift space. So this is the Markov thing. And the transformation we build is, so it goes from that space to that space. So I guess cross S to the N. The map is taking, I guess, XY to, so you apply the first element of Y inverse to X as like in action. And here you take the shift map, so shift of Y. And somehow the backwards ergodic theorem for this transformation provides after some averaging and using mixing. So we use this thing is mixing.
Yes.
But yeah, we haven't thought about any like mixing results, or as you said, the spectral gap results. Like this, this needs to be analyzed. It's very new.
Okay, thank you.
Thank you.
Are there any other questions? Well, if there are no other questions, let's thank Anush once again.
Thank you.
And thank you very much, everyone, for coming. Happy New Year, and have a good semester and everything. Okay.
Thanks, you too, and thanks for having me over again.
No, thanks a lot for giving a talk.
Great talk, Anush.
Thank
Thanks.
you.
Very nice talk. Bye.